Okay, so, yeah, hello. Okay, so before we start, I'm just going to pass on this sign-up sheet for people who may want to take trips to the city or also possibly take a trip to Mysore on Saturday. So there's two sides to this. Look at the options and put your name on whichever ones you find interesting. So we continue with our afternoon session. We are very happy to have Ron Donagi. He will be giving an introduction to Geometric Langlands.
Thank you very much, Aswin. Is the microphone working? Can people hear me?
The volume is not.
Do you want to adjust that? How about now? Okay. So great to be in India, in Bangalore. I'm going to be giving 3 talks about an introduction to the geometric Langlands theory. And these will be continued next week by Tony Pantev, who will talk about some specific cases where you can really see it in action with full details. The geometric Langlands conjecture is a non-abelian version of something that I hope people will recognize, will know well. Is there white chalk? I guess I'll use yellow. So, the Langlands program in general is a non-abelian version of CFT, which does not stand for conformal field theory, but for class field theory, as in number theory. So there's an arithmetic theory of class field theory, goes back to the 19th century, and this is a non-abelian formulation, generalization of that. Yes? Larger, okay. The geometric Langlands conjecture is a geometric version of the Langlands program, the Langlands conjectures. And you can think of that as a non-abelian generalization of the theory of curves and their Jacobians. So you can think of class field theory as an arithmetic version of Riemann surfaces and their Jacobians, and the general Langlands program is a non-abelian generalization of the arithmetic version. Geometric Langlands is a corresponding generalization of the theory of curves and Jacobians. So I'm going to start by reminding you what this story is. Yes? Jacobians? I apologize for my terrible handwriting. That's how I erase. Okay. So let's start by talking about Riemann surfaces. So C is going to be a Riemann surface, compact, smooth, curved, genus G. And to it, we associate the Jacobian, J of C. Yeah, thank you very much. Just leave that. The white will be more visible?
Yes.
Okay, thank you. So one definition of the Jacobian is you write it as the cohomology of the curve with C star coefficients, so with complex coefficients. The star should be outside, divided by H10 and by H1 integer. So if C is a curve of genus G, its cohomology has rank 2G. The cohomology with complex coefficients is a vector space with dimension 2G. So is the dual. It has a Hodge decomposition into holomorphic and anti-holomorphic. You divide by all the holomorphic stuff and all the integer stuff. Dividing by the integer stuff basically means you're taking cohomology with coefficients in C star, and then you still divide by the holomorphic part. So that's the Jacobian. There are many ways to define it. I guess this will be H lower 1, right? Because it's contained in the dual. I want it to be in the dual of H upper 1. Or another way of saying it is that it is H10 dual divided by H lower 1 with integer coefficients. So it's a vector space with complex dimension G divided by a full lattice, and that's what gives you a complex torus. What's going to be important to us is that there's an inclusion map, which is really given by integration. It's a map from the curve to its Jacobian. So you pick a base point P0, and then it sends a point P to integration from P0 to P. What does that mean? Well, choose any path from P0 to P. Integration on it is a linear function on harmonic one forms that represent the cohomology. So it gives you a linear function here. It's not quite well defined because you had to choose a path. If you choose the path, if you change the path, you're changing it by a loop. So it's not well defined in the whole thing, but it's well defined in the Jacobian. So we have a map like this. If the genus is bigger than 0, then this map is actually an embedding. So the curve sits inside its Jacobian. The problem is it depends on the choice of the base point. So a better version is to replace the Jacobian by the Poincare group. The Poincare group of C is non-canonically isomorphic to the integers cross the Jacobian of C. But this is not very natural. So a better way to define it is it's the set of all divisors modulo linear equivalence. Or in other words, it's isomorphism classes of line bundles on the curve. The integer part gives you the degree of the line bundle. The degree 0 piece gives you the Jacobian. Then the other degrees give you components that are isomorphic to the Jacobian, but not naturally. A choice of the isomorphism depends on a base point. So then we have a natural embedding of C, not to pick 0, but to pick 1, the component of degree 1 bundles, by sending the point that I was calling P to the line bundle OC of P. And then if you want to go to the Jacobian, that means you want to identify pick 1 with pick 0. That requires a choice of a base point. So this definition is better because it is intrinsic. It does not depend on any choices. Yet another version of the same elementary story is that you can think of this as a map from C across the Picard to the Picard. You take a point P and a line bundle L, and you send it to the line bundle L tensor O of P. So it sends P, the component of degree D to the component of degree D plus 1. This version is the one that will generalize best to the non-abelian case. This will become the Hecke correspondence. But it's essentially equivalent to this inclusion here or to the Abel-Jacobi map over there. They're all the same. Okay. So now let's let G be any group. And let's define a G local system on C or in any topological space X to be a representation rho from pi 1 of X to G. So we've seen these things in Saito's talk and in Abe's talk. To such a representation, you can associate a geometric object. Well, you really need something on which G acts. So you could take G to act on itself, and then you have a principal bundle. Or you can take some vector space on which G is represented, and then you get a vector bundle. So in the case that G is GL and C, the Riemann-Hilbert correspondence tells you that with some caveats, a G local system is essentially equivalent to a vector bundle of rank n plus a flat connection. In the case that X is a curve, you don't have to worry about flatness because there are no two forms. Every connection is flat. In higher dimension, that becomes important. So the abelian or baby version of the geometric Langlands conjecture says that for abelian groups G, I upper star, where I is, let's say, this map, the Abel-Jacobi map from the curve to its Jacobian, you can think of it as a map from log JG to log CG. So C is a curve, J is its Jacobian, what I was calling J of C. Log JG means G local system, a set of isomorphism classes of G local systems on J. Whenever you have a map, you can pull back the local systems. The abelian version of geometric Langlands conjecture says that this is an isomorphism. So at the moment, I'm thinking of these just as sets, but you can make them into, well, in the abelian case, these are actually manifolds. So they're as nice as possible, and these are isomorphisms of manifolds. Okay, let's prove something. Let's prove it twice. First proof. Pi 1 of J is the thing that I divided by. I took something contractible and divided by a lattice that's acting freely. So it is H1CZ, which is the same as pi 1 divided by commutators. It's the abelianization of pi 1. So any row from pi 1 of C to G factors through pi 1 modulo brackets, which is H1, which is pi1 of the Jacobian. So that says that any local system on the curve extends uniquely to a local system on the Jacobian, as long as your structure group is commutative, like C star. Okay, well, that wasn't very hard. Where does that fail if the group is non-abelian? Well, the representation will not be trivial on commutators. Okay, second proof. So it has the disadvantage that it's less crystal clear than this short argument. It has the advantage that it's algebraic and therefore it works over other fields, other characteristics, whatever, if you care about such things. So start with the d symmetric product of the curve. It's a manifold of dimension d. It's the same as the Cartesian product divided by the action of the symmetric group. The Abel-Jacobi map, or maybe it's better now to think about the Picard version. There's an I from C to pick 1. It extends to a map from sim D of the curve to pick D. So there's a map to pick D of the curve, sending a D tuple, P1 through PD, to the line bundle O of the sum of those points. That's the obvious map. What can you say about the image? It's very complicated for low D, but for D sufficiently large, this is surjective and proper. In fact, not just that, but it becomes a fibration. And you can say exactly what the fibers are. The fibers are going to be projective spaces. Well, that's true even if D is not large. Every fiber of this map is a projective space. The fiber over a line bundle L is the projectivization of the space of global sections of L. So it's always a projective space. It could be empty, but if it's not empty, it's a projective space. And in this case, it will be of dimension the difference. The dimension here is G. The dimension here is D. So it will be a projective space of dimension D minus G. This is only true when D is sufficiently large to be in what's called the stable range in the Riemann-Roch theorem. In general, the dimension will depend on L, but if the degree of L is sufficiently large, bigger than 2G minus 1 or something, then all line bundles of that degree have the same dimensional space of sections. So this is just a bundle. Okay, so a local system L on C determines a local system LD on the d-th symmetric product. A point of the symmetric product is a d-tuple of points. Just take the tensor product of those lines. That gives you a line that you associate to that point, and it moves around. So that gives you a well-defined local system on the symmetric product. For every D, in particular, it works for sufficiently large D. But if this thing is a fiber bundle, and the fibers are projective spaces, which are simply connected, the local system will have to be trivial on each fiber, so it descends to a local system on pick D. So for D sufficiently large, LD is trivial on fibers. So it descends to a local system on pick D of the curve. And then you have to do a little more work to show that the different pick Ds are isomorphic to each other, and the local system that you get, the different local systems that you get for different Ds all correspond to each other, so you really get a unique, well-defined object. So I'll skip the details. So you have to do a little more work. But basically, this gives you the local system on the part of pick D that involves sufficiently high degrees, and you have to say that it's actually the same on all sufficiently high degrees, and therefore you can use the same definition to push it down to negative degrees as well. Here is a reformulation. I'm going to need a lot more chalk, I see. I've just gone through.
There's a box somewhere.
There is a, yes. Thank you, that's excellent. Thank you. Okay, so the reformulation is, unfortunately I called all my maps I, so let's change the name. Let's take this map. Fortunately, I haven't given it a name. Good. So we'll call it H for Hecke. So I is some restriction of H to some piece. So for every abelian local system L on C, there exists another abelian local system, let's call it C of L, on the Jacobian, or sorry, on the Picard. Such that H upper star of the thing on the Picard. Okay, so H was a map from C across the Picard to the Picard. And I'm claiming that there exists something natural on the Picard. And naturality is going to mean the following. You pull it back, you have something on the product. And that something is going to be what's called the external tensor product of something on the left and something on the right. So in other words, it's projection 1 upper star of something on C. That something will be L. Tensor with the projection 2 upper star of something on the Picard, and that will be C of L. So this is an eigenfunction, eigenvalue property. It says that L behaves like an eigenvalue, and C of L behaves like an eigenvector or eigenfunction or eigensheaf in this case. So it says that for every local system L, there exists a local system C of L, which is an eigensheaf with eigenvalue L. So in the abelian case, all these formulations are equivalent to each other, and you can keep yourself busy going between them and doing the translation. This version is the one that has a chance of extending in general. So let's try to generalize it. Excellent. I was hoping somebody would ask that. So in the first proof, it's clear where I use the fact that G is abelian. Where did I use it in the second proof? Yeah. So what about SIMD? Right. So Yes. So yeah, that's the issue. So start with C cross C going to sim 2 of C, and it only gets worse in higher degree. So if we have a rank 1 system here, and I wrote something which I said was the fiber of the first pullback of projection 1 upper star of L, tensor projection 2 upper star of L. That gives me a well-defined sheaf on C cross C. Does it descend to sim 2 of C? Well, sure. There's a natural isomorphism from this to what you get by switching them. A tensor B is the same as B tensor A. But on fixed points, this map may be the identity and may not be the identity. In the case that L is a line, it will always be the identity. You don't have to worry about it. But if L is a vector space of high dimension, so I'll write V instead of L. So you're saying take V, tensor V, and take the map that changes the two factors. There's a symmetric part and a wedge part. On the wedge part, it's anti-symmetric, so that one does not descend. So you get that the part that is invariant is not locally is not of constant rank. The rank drops on the fixed above the fixed point, so you're not getting a local system. So that's where we use the fact that it's rank 1 really. The general abelian case can be reduced to the rank 1 case. Well, you could use the Cartesian product, but then the fibers here do not regularize. The fibers will be finite covers of the projective space, and they turn out to be non-simply connected. So the descent argument will fail. The branched covers of the projective space branch along something messy. So there's something very special about the symmetric product. That's the only one that works. Other questions? Okay. How am I doing on time? Thank you. That's time remaining. Great. Okay. Okay. So the geometric Langlands conjecture is a hoped-for generalization of this to the non-abelian case. So we still have a curve C in the picture. The Picard gets replaced by Bun. So instead of the group being essentially GL1 or C star, you could take your group to be GLN. You could take it to be any complex reductive group. SON, C, things like that. So Bun is the moduli space of G bundles on the curve. And immediately somebody should raise their hand and ask, are you talking about the moduli space or the moduli stack? Well, you really need the stack. So the correct version of geometric Langlands forces you to look at the stacks. It's often easier to start with the space and then move to the stack a little later. But when I write Bun, I am going to mean the moduli stack of G bundles. So that avoids the kind of issue that we saw this morning where they had to choose some finite cover of the moduli space in order to have a universal object over it. The stack, by its definition, essentially has a universal object over it. Okay, so the Abel-Jacobi map, this I, or the thing that I was already calling H, let's just call it Abel-Jacobi, is replaced by Hecke. So the version of I that I'm going to use is this one. The replacement is not really a map. It's a correspondence. So I should say that the map gets replaced by a correspondence. A correspondence between X and Y means a subspace, scheme, stack, whatever structures these are, a sub-object of the product is called a correspondence. You might want to require that the projections in both directions are proper, or at least in one direction should be proper. So given an H in X cross Y, it gives you H lower star from things on X to things on Y, and an H upper star that goes backwards from things on Y to things on X. So if you think of H itself as mapping to X and mapping to Y, with P1 and P2 being the maps, you can start with some object on X, take P1 upper star, and then take P2 lower star. In whatever category you're working, of course, you'll have to make sense of it. So if you want to go from X to Y, you need to know that P2 is proper so you can push forward under it. And if you want to go from Y to X, you need to know that P1 is proper. Okay. So any map gives you a correspondence. Just take the graph of the map. So a correspondence is a generalization of a map. It induces maps on homology, cohomology, Picard varieties, not quite Picard varieties, but on derived categories of coherent sheaves, things like that. Okay. So instead of an Abel-Jacobi map, we're going to get a Hecke correspondence. The Hecke correspondence
the domain, by domain I mean the projection onto the first step. Projective on that or
projective?
bijective?
No, definitely not. Definitely not. So just wait a second. I'm going to show you what this does. So a typical example is X might be a surface, Y might be a surface, and H might be a threefold contained in the product. So you have curved fibers this way and curved fibers that way. So the projections are definitely non-trivial in both directions. By the way, this notion of correspondence is it used to be a big thing. Everybody in the 19th century studying mathematics learned about correspondences. If you look at an old book like Semple and Roth or Hodge and Pedot, they have chapter after chapter describing the actions of correspondences. And they use correspondences to define the Jacobian. So somehow correspondence seems like a more basic object to them than a linear equivalence of divisors. Anyway, the Hecke correspondence, let's call it Hecke for now, but I'll just it will soon become just H. So the Hecke correspondence is a correspondence from pick, no it's not, from Bun to C cross Bun. Right? This Hecke correspondence was, or maybe I should have, let's put the C on this side. So it will look more like this. The Abelian case was an actual map from C cross pick to pick, I'm replacing pick by bun, and I'm forced to replace the map by a correspondence. So all I know is that this new H, this new Hecke, is going to be some subvariety of the product. So it's really contained in C cross bun cross bun. So Hecke will be the set of triples P, V, and V prime, where P is a point of the curve, V and V prime are bundles, and V prime is a modification of V at the point P. In other words, V prime, let's say, contains V and is contained in V twisted by P, or something like that. This terminology makes sense when V is a vector bundle. If you'd like to get the story to work in full generality, where G is just a reductive group, you have to work a little harder. Maybe I'll just give a quick outline of what you need, and I'll leave it for you to think about. Or for more general G, you want really quadruples, P, V, V prime, and beta, where beta is an isomorphism from V restricted to C minus the point to V prime restricted to C minus the point. So you just want two principal G bundles, V and V prime. So just away from the point, they're isomorphic, but the isomorphism is allowed to blow up at the point to arbitrary rank. The problem with the set of these data is that it's not proper. It's not a finite type, because I'm not putting any bound on the order to which the isomorphism is allowed to blow up. So you really need to truncate it by pieces of finite dimension. This thing has infinite dimension. So let me delay that till tomorrow. So there's a formal way you do it. It turns out that the set of reasonable truncations is indexed by the co-roots of the group G that you're using. There's a well-developed theory of that, but it's probably a little too sophisticated for a first talk. So we'll just keep the vector bundle version and some faith that it can be generalized. Yeah, it's just not going to be true if you're losing stability.
I think that that is true, that if you modify the vector bundle, which is stable, you might get something which is not stable. And so I think that this means that the projections are not there proper. So
yeah.
That will be
So that's one way to state the issue. Okay. So one version of the geometric Langlands conjecture says that for every local system, I guess I'll still call it L, on C, there exists a local system C of L on Bun, such that Hecke upper star, the Hecke transform of C of L is going to be L external tensor with C of L. This tensor in a box means projection 1 upper star of the first, ordinary tensor with projection 2 upper star of the second. Okay. So there are still several things here that aren't quite right. One thing that I'm hiding here is the group. So for every local system L on C with structure group G, there exists a local system CL on Bun, but it's not Bun with structure group G, it's Bun with structure group, the Langlands dual of G. GLN happens to be one of the few cases where the Langlands dual of the group is itself. So for vector bundles, I don't have to worry about it. But if I'm going to do it for other reductive groups, you have to know what the Langlands dual group is. I'll talk about that a little bit tomorrow in the second talk into this. The other issue is that this is not going to be a local system. A little bit of the problem is the difference between the stack and the moduli space. A related issue is the fact that the moduli space tends to be singular. There are bundles that have automorphisms or cohomology jumps. So certainly on those loci, you don't expect the behavior to be as nice as what we had in the Abelian case, where we were working on the Jacobian or the Picard, those were smooth manifolds. So clearly, you expect trouble where these things become singular. But it turns out that it's actually worse, that even on some smooth parts of the locus of bundles, you expect these things to change rank. So the correct notion to put here is a perverse sheaf. A perverse sheaf is to a sheaf more or less as a skew field is to a field. In other words, it isn't. Perverse sheaf is not a sheaf. It's a complex of sheaves. It's an object of the derived category, which in some sense behaves as if it were a sheaf. It's in a different triangulation of the category, in a different core. But what you need to know is, for any local system on a Zariski open subset of anything, there is a unique extension to a perverse sheaf on the whole thing. So whatever perverse sheaves are, specifying them is the same as specifying a Zariski open subset on which the thing is going to be a local system. And then it somehow knows how to account for the possible jumps in the local system. So I'm not going to get into more details about what a perverse sheaf is. We'll just treat it as a local system on a Zariski open subset. Okay. So now we have to make a decision. I told you, at least at some elementary level, what the geometric Langlands conjecture says. So one decision is, do you want to know what the non-geometric Langlands conjecture is, or shall we just ignore that because it's not going to be relevant for anything else that I'll say for the rest of the week? But just for historical context, I can make a detour for a few minutes to talk about that. All right, let me try to talk about it without writing on the board then. Okay, I'll just enumerate other versions. So C, what's crucial about it is that it's one-dimensional. The other versions look for other one-dimensional objects. So C, which is a Riemann surface, could be replaced by C, which is a curve over a finite field. And that turns out to be a fairly reasonably minor modification. You can imagine that if you know the language of algebraic geometry, or whatever you can do in a compact curve, you should be able to do over finite fields. A much more drastic change is to take other one-dimensional rings, like the integers, or any maximal order in a number field. And that brings you closer to the original Langlands conjecture. So the non-geometric conjecture has to do with things like this, rings like the integers. So what does it say? Well, let's just try by hand to go through this and change all the words where we're replacing the curve C by the integers. Let's see if we can do that. So what replaces, let's skip that for a moment. Our input is going to, our starting point is going to be a local system on the curve. What's a local system with the integers? Well, what's a local system on the curve? So we have assigning to each point a vector space, and somehow it moves in some uniform way. Okay, so what's a point of what so when we're replacing the curve by the integers, what do we replace points by? Prime numbers. So a point becomes a prime, and a divisor becomes an integer, a product of primes. Okay, so we need some way of assigning to each prime a vector space over the residue field of that prime, so something like so to prime P, you want a vector space over the p-adix, something like that. I'm sorry? Yeah, of course, I mean spec Z. Yeah. Okay. Thank you. So, yeah, so what's some uniform construction that to each prime assigns a vector space of some fixed rank over the p-adix? Want it to be uniform but non-trivial. Okay, here's a geometric way of doing it. Start with an elliptic curve defined over the integers. For each p, you can look at the Tate module, the set of all points on the elliptic curve whose order is the power of p. That's going, well, at least for the good primes, that's going to give you a vector space of rank 2 over the p-adix. Except you'll have some supersingular primes, whatever, where this thing vanishes. So the story that you get is really going to be an analog of the ramified geometric Langlands conjecture, which I haven't quite told you about, but try to imagine it. Okay, so one way to replace, okay. So the curve heuristically becomes spec Z. A point becomes a prime. A local system, let's say a rank 2 local system, becomes an elliptic curve. Okay. So now what is Langlands supposed to tell us? That given a local system on the curve on spec Z, we get a local system or a perverse sheaf or something over some moduli space. So what will Bun become? Well, it'll become the moduli of elliptic curves. So it'll become some modular curve. And if you start playing with it, you find out that there's a natural modular curve in the picture. So a modular curve is the moduli space of, well, it's the upper half plane divided by a congruence subgroup, which is the same as the modular of elliptic curves, together with the basis of points of some order. So that order is called the conductor, and it's somehow determined for you in a natural way by the original local system you started. And then, so at the end of the day, what is this part of the non-geometric Langlands conjecture going to tell you? It's going to tell you that starting with an elliptic curve, you're going to find some data on some modular curve. When you unravel it, it tells you that there's going to be a map from this modular curve to the elliptic curve. So this was the conjecture of Shimura Taniyama, proved as part of the proof of Fermat's last theorem. So that is a typical special case of the arithmetic Langlands conjecture, which is not covered by the geometric Langlands conjecture, although it clearly has a lot of geometric content, but of a different type. Okay, that's as much as I'll say about other Langlandses. Well, that's what becomes the existence of a map between from the modular curve to the elliptic curve. So maybe let me tell you a little bit about what to do in the ramified case. So this is ramified abelian geometric Langlands. So we start with a curve C and divisor D. And instead of local systems on the curve, we look at local systems on the complement of the divisor with some reasonably nice behavior around the point. That behavior is going to be tameness, which, if you go through the Riemann-Hilbert correspondence, which we saw this morning, tameness will say that the connection has first-order poles rather than a priori it could have had arbitrary order poles. Okay, so what's going to replace the Jacobian, or more generally, the Picard curve, the Picard group of the curve? What should be the generalization of that? So, well, one way to think about it is that this thing parameterizes line bundles, or divisors on the curve modulo linear equivalence. So instead, we can look at divisors on the curve whose support is away from D, modulo the right notion of linear equivalence. You have to think about that for a moment, but the right notion is, you say that two divisors are linearly equivalent if the difference is the divisor of a function whose value is 1 at each point of D. So you require that your function is the unit 1 at the specified points. Right, both of the divisors are disjoint from D, so that doesn't cause a problem. So there's a notion of linear equivalence for divisors on a punctured curve, and that leads to the notion of a generalized Jacobian or generalized Picard variety. I think it's due to Rosenlicht and someone else. I forget, there's a book of Lang from 50 years ago where he talks about generalized Jacobians. A little more geometrically, here's what you're doing. Let C bar be what you get from C by collapsing the divisor D. So you take all the points of D and identify them with each other. It's not quite as innocent as it seems. So if you're gluing 2 points, you just have a normal crossing. It's just an ordinary node. But when you have 3 points, the thing is no longer locally planar. The tangent cone is going to be the tangent space will be 3-dimensional. It'll have 3 independent directions for the 3 branches, and so on. So it's a little tricky, but anyway, you're just doing the obvious thing, just identify the points with no conditions on any higher derivatives. And you're just taking the Picard of C bar. So just honest line bundles, not torsion-free sheaves or anything, just honest line bundles on the singular curve. So that's the notion of the generalized Picard. Anyway, we have a map eta from C minus D cross pick of C bar to pick of C bar, which just takes a point in a line bundle and goes to the line bundle tensor with O of the point, same as before. So it's the Abel-Jacobi map. But the problem is eta does not extend to C bar or even to C itself. If you try to approach one of the points of the divisor D, the thing goes to the boundary of the Picard of C bar. So you need to, right? So what we're trying to do is now say that the local system on C minus D, so it's a local system that has some local monodromy around those points, should extend to a local system on some version of the Picard or the Jacobian, right? But the problem is that the natural Abel-Jacobi map does not extend. So somehow you're trying to turn the disadvantage into an advantage. So here's what you need to do. You observe that there's a natural map from pick C bar to pick C. Just forget the marked divisor. A line bundle goes to a line bundle. It's a torsor where capital T is isomorphic to C to the, what did I call it? K minus 1. K is the number of points. So more precisely, let's look at the map from Z to the K, going to Z, the sum map. Take a K-tuple of integers and send them to the sum. Did I make some mistake? Let K be the kernel of this map. So it's K-tuples that add up to 0. And let T be homomorphisms from this K to C star. So that's this torus. It's isomorphic, not naturally, to C star to the K minus 1. K minus 1, yeah. So I'm saying that this is a bundle, and each of the fibers looks like this. In fact, if you want to say more canonically, you have a projection P from the Picard cross the divisor to the Picard. On the Picard cross the curve, there's a natural universal line bundle. It's called the Poincare bundle, so I'll call it script P. It's a line bundle on the curve cross Picard with the property that its restriction to each point here across the curve is a line bundle on the curve given by that point in the Picard. So it's this morning it was called the universal bundle. So take this Poincare bundle, restrict it to the Picard cross D instead of Picard cross C. So that's a copy that has K copies of a line and push it forward. So now it's on the Picard and divided by a diagonal action of C star. So this gives you global formula for what this generalized Jacobian is. You can just unravel from the construction that this is equivalent. Okay, so there's a natural way to compactify it, to get a compactified Jacobian. The problem is these fibers are tori, non-compact tori. So in particular, pick bar is non-compact. It's missing divisors at infinity. And you simply take pick bar. This torus acts on it. Each fiber is a torus over it. And instead, you replace the torus by projective space of dimension k minus 1. T acts naturally in the projective space in an equivariant way. So this is, we'll call it pick plus. So this is a natural compactification of the generalized Jacobian. And this is the right object to work with. So the map that I had before, eta, extends to, let's call it eta plus, from C to pick plus. Is that what I wanted to say? Sorry, C cos. Pick plus to pick plus. The map is still slightly irrational. There's a small locus that gets blown up, but it has large codimensions. So let me just ignore it. It's not going to affect what I'm going to say. And if del is the boundary, it's pick plus minus pick bar. So that's the stuff that we had to add. Then you can convince yourself that eta plus inverse of del is the union of two things. One is D cross pick plus, and the other is C cross del. So that in particular explains why eta itself does not extend, because as soon as you're going into one of the points of the divisor D, you're going to the boundary, not to the interior. So you cannot extend across any point of the divisor D. Anyway, the tamely ramified version of Abelian Geometric Langlands conjecture, it's not a conjecture, it's a fairly easy theorem, says that every ramified Abelian GLC says that for every tamely ramified local Abelian local system L on the curve C with tame ramification along this given divisor D, there should exist a C of L, which is going to be a tamely ramified local system on pick plus, ramified along this del, along the boundary, such that the thing in the box, the thing in this box holds. So you can extend Langlands to the ramified case, but you have to modify what you mean by the Picard or the modular bundles. Okay, so let me just use my last couple of minutes to tell you what's coming, and also to say a word about how to connect this with the parabolic story that we heard this morning. So the full version of Langlands is going to involve parabolic stuff. Fortunately, by the time I get to it, we will have heard enough about parabolic stuff that I'll be able to use that. But in the abelian case, which is what I was emphasizing today, you don't need to state the parabolic stuff explicitly. You can just talk about ramified stuff. So the ramified stuff is a simplified version of the parabolic stuff, which in the abelian case is equivalent to the full story. So what I want to do is to add a few more details about the precise formulation of geometric Langlands in the non-abelian case. Sketch Hitchin's construction of his integrable system, talk about speckle covers and things like that, and explain a sense in which this can be used to abelianize the non-abelian geometric Langlands program. I have to say, back in 1988, I think it was, I was visiting Arnaud Bourvil in Paris, and I was telling him what I was doing, and he was telling me about his stuff, and he was telling me that he was writing this paper with Narasimhan and Ramanan on Hitchin's system, and I had never heard of Hitchin's systems. He said, "Oh, have a look. It's going to appear in this volume, in this birthday volume of Duke in honor of Manin's birthday." So I looked there, and yeah, there was this paper by Hitchin, and right next to it there was a paper by Lomon on the nilpotent cone, and that's where I learned about the Langlands conjecture. And 30 years later, basically tried to put these two papers together and trying to carry out ideas that were implicit in that volume from 30 years ago. So I'm going to tell you about the Hitchin system. I'm going to maybe add a few details to what we've already heard about the non-abelian Hodge, the high-dimensional version of Riemann-Hilbert, the equivalence between representations of the fundamental group, flat connections, and Higgs bundles, which are the things that occur in the Hitchin system. And then I will try to outline in some detail a program for trying to prove the geometric Langlands conjecture in general by basically by twisting it through the non-abelian Hodge correspondence. And then next week, Tony will talk about one or maybe two special cases where we can actually carry this out. And you'll see the geometry of the Hecke correspondence, and you'll see the loci where the sheaf that you're looking for in Bunn fails to be a local system. It becomes just a perverse sheaf. That's what we call the wobbly locus. So hopefully these things will become concrete by the end of the 2 weeks. So thank you for your time.
Questions, please.
So this is it working?
Just speak loudly.
Singular supports, does that appear at this level, or do you only see that when you, can you already explain in this context why?
Right. So the question was about the occurrence of singular supports. In the version that I stated today, they do not occur. There are fancier versions of geometric Langlands. So the version I stated says, for every local system, I have an object on the other side. The generalization says, think of loc, the space of local systems. Think of our local system as a point there, or better yet, think of it as a structure sheaf of that point. And ask what happens for other sheaves on loc. So the version that I'm going to state formally next time says that there's an equivalence of derived categories between the derived category of coherent sheaves on loc and the derived category of D-modules, which are essentially the same as perverse sheaves, on Bunn for a pair of Langlands dual groups. And that's the version that has been around in the literature for a long time. The only little problem with it is that it's false. And Dennis Gadsgoy has been going around for a long time checking cases of that and trying to understand the extent to which it is false and how to fix it. And the problem is that there are too many sheaves on lock to have a chance of all of them having corresponding objects on the other side. So you need to restrict the class of objects, and you restrict that by putting conditions on of singular support of the sheaf on lock. This is probably beyond what I will get to in these talks, but that's where the singular support fits into a derived category generalization of the more elementary story that I was trying to present today.
Structure sheets of points are in this model.
So the structure sheaf of a smooth point of lock is always going to be there. The question is, what happens if your point is not quite a smooth point? If it's either a singular point or a stacky point in some sense, that's when it becomes unclear what do you mean by its structure sheaf. So your first attempt is to look at all sheaves supported at that point, but there are too many of them. So it turns out you want the support to be the point and the singular support, which is like the support of the microlocal extension, to also have to be in the nilpotent cone. So that's essentially their Arinkin Guide-Scory result.
Other questions? Actually, I had a question. So maybe this is overkill for the abelian case. Is there a sense in which, if you understood, say, the ramified Langlands for some low genus Riemann surface, you can use that to kind of bootstrap the proof for higher genus Riemann surface or something like that?
Wouldn't that be nice?
Maybe the abelian case would be the easiest way to check if something like that is true. I don't know.
Yeah, even in the abelian case, I don't. I mean, in the rank one abelian case, I don't see how you can bootstrap the genus.
I'm basically trying to kind of put together a pair of pans with cylinders and build a higher genus Riemann surface, and somehow say that if I knew Langlands for pair of pans, then I can.
Well, you can get some higher genus Riemann surfaces as covers of a low genus Riemann surface, but you will never get the generic Riemann surface of high genus that way.
He's talking about gluing together.
Yeah, I think he's talking about the physics language. So you have like lower genus curves.
So it's talking about things like Knightsky, Moore, Gayoto.
Well, no, not even that complicated. Like just putting together a Riemann surface using just 3 punctured spheres and. Okay.
That would be great, but I don't know. I wouldn't know how to do that.
Okay. Any other questions? Okay, if not, we'll thank the speaker again.